Alright, we're going to see if we can get both of these things to work at once, though knowing in full which we won't be able to do, we just saw. Knowing in full reality, you've got to be able to do this, and you've got to be able to do it fast. You've got to take a step up now from just saying, well, you know, I did all that math, it really didn't mean anything. So I'm going to put a point out here and a force, and I'm going to be extremely arbitrary. I'm going to say that point is at 5 and 4, and it has a direction of 25 degrees. Now what I could have said or should have said is it had a change in y and a change in x and come to 25 degrees. But let's just say that you know from the formula y equals mx plus b is the same as y equals the tangent of theta times x plus b, which means that you know immediately that you can go from a point slope formula that says this: m, the slope, equals any arbitrary y minus y1, which was y1 is 4, over any arbitrary x minus x1, which is 5. Y equals mx, right, plus b. But now this is called point slope format, and now you just got to know what m is. So what you look at here is the tangent of 25 times x minus 5 equals y minus 4. And then in fact you know that, because what you're trying to calculate, just so you know in this, is you're trying to get the slope intercept, whatever that is, so that you can offset through the 0 point for any number of reasons. You know, any number of reasons. You've got to be able to do that kind of basic offset. You're going to do it in CAD, but you're going to realize it's going to turn out to be a cosine thing here. So what you got here is the tangent of 25, which you don't know. I coulda, woulda, shoulda, and when you're doing these problems, try to do them with something that you know the number to. So to go with the tangent of 25, we'll continue to solve this out. So this is actually this. I'm going to close this thing up here. Again, we're looking for the offset distance here for any number of reasons. Most specifically in this case, so we can actually figure out what is the torque of that force about the 0, 0 point. So what you've got now is the slope is going to be, as we saw, y equals mx plus b. We just need to find the slope intercept so we can multiply it by the cosine of the angle. So let's see if we can do that. So we have now, we're going to, and I need to do this. That's what I missed. Okay, so now what we have is y equals mx. So tangent of 25 degrees times x minus the tangent of 25 times 5, and then plus 4 equals y. And now we have the mx, and so we now know that the slope intercept b is equal to 4 minus the tangent of 25 times x. And if you know that, start realizing you know the tangent of 30, you can start get something in it. But now let's see if we can flip out this calculator and get it to work. Okay, there it is. Remember, checking the mode. You would have a check anyway, even if you didn't check the mode, because you should know about what the tangent of 25 is. It's a little bit less than 1 over the square root of 3. But that said, I'm going to hit enter here, second quit. We know that you can take the tangent of 25 times 5. We want to negative that. We want a negative second answer here. We want the negative of that plus 4. And that gets me the slope intercept. Now the slope intercept is the number we have to multiply by the cosine of 25 degrees. So we're going to take this times the cosine of 25 degrees. And you're going to have an offset of 1.5121. So we're going to offset B, we said, was 2.33. To go back to this again, and the offset is 1.51. Offset equals 1.51. Now let's remember that as we go into CAD here. I'm going to just see if I can do that right on top. We expected if we were going to get 5,4 at 25 degrees, our offset would be 1.51. How did we do it? We wrote the equation, found the slope-intercept, and multiplied by the cosine of the line that defines the direction of the line. So let me see if I can minimize this, go right into AutoCAD without, giving too many conniptions here. And this is the type, that one problem is the kind of the first one I'm going to say to stick in your head. It's extremely useful. You're going to see later that it's great for, it's essentially a vector projection problem amongst other things, but I'm going to go now here immediately into AutoCAD if it opens, which it might or might not. And I'm going to draft that 5,4. I'm going to go here, hopefully. Alright, now I'm in AutoCAD. So what am I going to do? I'm going to say hopefully if this keyboard is working, I'm going to say a line from 5,4, and then I'm going to say at any distance at an angle of 25 and then go from there. So I'm going to say line from 5, 4, waiting for it to find my keyboard. There it is. 5, 4. And then at, I'll just make it 100 at an angle of 25 degrees. And what was our, now I'm going to offset this, offset through, select object to offset through what point? 0, 0. I'm going to go line from near perp, and again you're expecting 1.51, and that's what you get. You do that a few times, you use it on a regular basis, you'll realize that you don't always go to the CAD, though you always have CAD as this nice, sometimes faster, but sometimes just a redundant calculation. So what did we do here? We wrote the equation of the line, we figured out the slope-intercept, and we multiplied the slope-intercept times the cosine of the direction of the line, and that gave us the off distance through the 0, 0 point. Put that in your head, practice it. It's going to make things extremely easy and useful when you're trying to figure out torques or moments of forces that are kind of floating out in space. You'll see what makes this easier sometimes is to shift your 0, 0 point, your user coordinate system. That's what we learn matrix algebra for. Thanks for listening.